position, that you're going to get a beam that's perpendicular to the length of the array, and it's also going to be a fan type pattern. And going across the array, you're going to follow this red line because the array is only one element wide. So it's going to be a very smooth pattern. Going down the length of the array, you've got the interference between the different elements. So you get the side lobes, which you see in the blue line. And those two lines here track kind of following these arcs around the polar pattern of the array there. And that's just saying the obvious, I guess. This is a different kind of antenna, standing wave slot array. This was used in most of the fighter aircraft back in the 80s that were being built by Hughes. Very unique. This is a waveguide. It's just a piece of rectangular metal hollow that you put energy in one end, and as the energy flows down there, it leaks out through these slots that are shown. And the slots are put in different positions that control how much energy is getting out the slot, and also what the phase is of the energy that's getting out that slot. So you can control all sorts of patterns by using this sort of thing. And what's great about it is you can add all these things together, and I'll show you an example. Now my point here is that with the arrays, in that time, that was an F-15 fighter, you had the array face, which was out in front. It had to be controlled with a gimbal. And it had this array face had a gain of about 4,000, but it also had a beam that's about 2.5 degrees in width. So if you're looking out into space, how do you know where to look? You can look anywhere, but how do you know where to look? Okay? You have to be able to move it in a gimbal, and you normally do scanning of the sky to try to spot something. That can take a long time. And you'll see in a minute the benefit of electronic scanning. This is what that array face looks like in an F-18. Okay, there's 684 elements in there. Each one of those slots has a specific phase and magnitude coming out of it to give a very unique shape to this beam that's coming off of the array. Now I've put two lines on this array. I added those on there to show that the array feed structure behind it is actually set up such that you can receive energy in either the top half and the bottom half, or the right half and the left half independently. And what that allows you to do using a system called monopulse direction finding with this array is what you can spot things in space and zero in on them really quickly. I can talk about that a little bit more when we're done. We've got a little time. But I took it out because it took too much to say directly. Now this will show us how we can do scanning. Scanning is being able to move the beam of the array without moving the array itself. Okay? So I'm going back to the same 6 elements, and I just have some of the parameters of the elements there. And what we need to know is what the delta phase is, what phasing you're going to put between the elements. Okay, so here's the one equation that's in this presentation. It can be solved very simply from that once you understand the geometry. But the point is that there's a delta phase you see down here, and the E1 is one port, and the E1 phase is the second port, and the delta phase is the difference between the 2 ports. And we have to know what that is. And with this equation, for a scan angle of 30 degrees, if that's where I want the beam to be looking, we set a delta phase of 116 degrees between these 2 elements, between these two. In other words, they accumulate all the way along there, okay? Now, I haven't brought up the term phase before, and I know that's got a lot of definitions, but with respect to this stuff, it only really means one thing, and that's the difference between two different waves, okay? So we call the first wave up there is a reference wave. That might be the number one wave on one of the elements. And then this particular wave I'm showing here has a 90-degree phase shift with respect to that. So it has a delta phase of 90 degrees. And that, whatever that shift is, you would shift it within the electronics, feeding the elements. It's only relevant in arrays because it has to be relative to something, a reference, and it's a single element. You don't have to worry about that. So here's a single element, doesn't matter what the phase is. This is 180-degree radiation off of that. Now if I put the same 6 elements and just made a little parallel plate kind of radiation situation with the 6 sources with them 116 degrees apart, and then put the scan pattern down at the bottom, you can see that this is scanned out, and right at 30 degrees, that's where the beam is. It turns out this is a 14-degree beam, but that's not related to the phase. That's related to the overall spacing and the elements themselves. And then the rest of the energy that's all up here, you got 6 times the amount of energy because you got 6 times the number of antennas, and then you've got energy in the side lobes and things like that. But that's how you get to change the position of the beam. So now we're talking something that's really massive. Although this is still a very small antenna, and you can think of it relative to the aircraft that had 684 or something like that electronically scanned. Well, that wasn't electronically scanned, but they are now, and we'll see that in a minute. This is an 8x8 antenna. This is something that I worked on for a company. This was back about 10 years ago. This is the main beam here, the gain of about 200. And we wanted this whole system to be able to scan out to 45 degrees in any direction. In fact, have a cone of space out to 45 degrees that you could place this beam in, okay? This is the result of the design, looking in one particular direction. And we see that we just did 4 plots showing at 15-degree steps up to 45 degrees. And what's good about that is that nothing else popped way up somewhere and destroyed this nice pattern that we had.
What was the application for this phase array?
Well, I'll show you in just a minute. Here's the answer to your question. Okay, these are the aircraft, F-16, F-18, all the way up F-15. And these are fully electronically scanned arrays. This shows you what you can do with it. No gimbals, no moving parts. You're not looking at this guy over here and then take a half a second to get your beam over here. You can move within milliseconds. And you can be looking at 14 different targets essentially simultaneously because it's so fast you can jump back and forth. And you can keep track of all these different targets. Of course, you're not seeing them all simultaneously, but in effect you're looking at this guy and then you're looking at this one and the difference. And then you can also attack you can control 6 different missiles coming off of your plane going after 6 of those targets just with one antenna. And all of that phase and electronic information is kept in big files. So, anyway, that's a key thing. So. Now, in summary, I'd like to tell you what I believe is the most amazing aspect about antennas. Only 160 years ago, a scientist named James Clerk Maxwell came up with a bunch of equations on radiation. And then it took 20 years for anybody to actually establish that he was right or wrong and prove that he was right. And then in only 9 years after that, Marconi came up with the radio. And today, I can take this cell phone and talk with just about anybody in the world because of what Maxwell did. In 160 years, it's not a long time. So, thank you very much. And
the question is, what are practical challenges when you're designing an antenna, let's say for satellites, for radar, or communication? What are the obstacles when you start to design for those different applications?
the biggest issue that's really that's hard to work on.
What did she say, Bob? I didn't hear her question.
She asked, what are the issues of complex antenna designs today? You know, and this, like I said, is very, very low level. I never even talked about what the impedance, what it looks like looking into the antennas. That's where the real effort is. Because as you're looking over frequency or having wide frequency bands, the impedance starts moving. And when the impedance moves, you don't get effective energy into the antenna. They have to be matched up, okay? And that's for single antennas. As soon as you start doing arrays, like these electronically scanned arrays, as you pull multiple antennas close together, they interfere with one another. It's called mutual coupling, and that's very complicated. And prior to computers, that was just totally limited. What guys could do was a few laboratory experiments that kind of gave them a feeling for what was going on, but could never do any of this stuff that's done today. It's all done with the computers. Question?
A dumb rudimentary question. Can you go to slide 35 for a second?
I think so. Let me see. Oh, this isn't working. It didn't let me use my computer. I could do that on my computer.
Next slide.
Is that the one?
Is this, we used to use, at least in the 2D space, Smith plots. Is this a 3D version of a Smith plot?
No, nothing
For
at all.
radiation, or for directionality for between a cardioid and omni with just a z-axis? Or no, this is not a Smith chart. It's not plotting radiation.
Not plotting impedance. This is radiation, not
Okay.
impedance.
Oh, not impedance. So
Impedance is
we don't know the amount of RF energy.
Well, if
Or
part of the design of this is to have it matched over that whole stand. Everything that you do is still well matched at each scanning angle at any direction. That's all part of the contract, so to speak, is to have it with a good match. But this is just the main beam and all the side lobes around it, okay? This is just a broadside pattern, okay? Now, if we cut down through one of the X or Y planes, and then we look at this pattern, this is what that pattern looks like with the main beam as we scan it in steps of 15 degrees, just to show that it can be done without destroying the rest of the field. So this is all pattern. I haven't ever
There's no
done
spurs or any other kinds
nothing.
of unintended harmonics or anything like that.
Right.
That's pure waveform.
Yes,
Into
in the pattern, in the beam.
Got it.
That's correct. And as soon as you try to, if we tried to scan that out to 60 degrees, I know over on this side, this stuff will be coming way up here and all sorts of funny stuff going on. All of that has to do with the spacing of the elements. That was all looked into at the very beginning. This pattern took 5 years to develop. Okay? And the first thing you look at is the size